In this video, we're going to explore some of the properties of integrals, remembering that it really, right now, for us, just represents a notation that means find the area. I also want to do just a brief review, real quick, on using our geometry. So this very first one, you see, it's 4. It's just 4, the function. We're finding the area from -2 to 3. So I put that over here. So -2 to 3 under the function 4. So you look at that, and you say, well, what's the area? Well, it's a rectangle, 4 units high, 5 units long, so it's 20. Now the next question says 4x from -2 to 3. So now we're focused on that blue line from -2 to +3. So we got a series of triangles here. Now this bottom triangle has a width, or a base of 2 and a height of 8. So 2 times 8 divided by 2 is 8. And remember, because it's below the axis, we probably want to think about it as negative. This other rectangle has a base of 3 and a height of 12. So 3 multiplied by 12 divided by 2 is 18. So we have -8 and 18. That makes this integral 10. Remember, the integral represents basically displacement. Okay, we had 8 units. If this were a velocity graph, we had 8 units backwards and 18 units forward for a displacement of 10. If you wanted to just say, how much area is bounded in there, remember that that would be represented by the absolute value of 4x. And then the answer would be +8 plus 18, so it would be 26. And that would answer the question, how much area is being bounded by that graph. But that's not what this was asking. Just simply the integral leaves the negatives in the problem. Okay. And finally, the last one, we're looking for the area under the screen curve right here. It's a semicircle. So semicircles, remember, are 1/2 pi r squared. In our case, the radius is 2. So 1/2 pi multiplied by 4 is 2 pi. This, I know because it's, it's going to be on YouTube that this might get a little bit fuzzy. This is in the book. I'm going to try and go through these rules as quickly as possible and just kind of explain them with an example. But they are in the book, and they're pretty easy things for the most part. So like this first example, I'm just going to use this little velocity graph here. Number 1, the order of integration. Well, we used this graph before, and if we do the integral of this velocity graph from 0 to 9, okay, hard to see, I know, but 0 to 9, the area we found in the last video when we used this was 100. What this says is that if you start at time 0 and you say, well, how far are they away 9 seconds later, the answer is they're 100 feet away. Okay, their displacement was 100. Well, rule number 1 here says if I were to reverse the bounds, the answer now would be -100. Okay, and the reason is what this new question, I'm basically restating the question. It used to be I'm at 0, 9 seconds later I'm at 100. Now the question is saying, okay, starting at 9, here I am starting at 9. Where was I at time 0? The answer is 100 feet back from where you started. So that's why the negative is there. Okay. All right, next. Let me grab this one this time. This next property talks about the fact that if I were to say I'm going to find the area, this is x squared, from, let's say, 1 to 1. How much area is there from 1 to 1? Well, the answer is 0. because there's a height there. Oh, 1 to 1, I've just drawn it at 2. There is a height there, but there's no width there. Okay, so it's impossible to say that there is any area, so we just say the area is 0. All right, constant multiple. Well, let me do this again. So I've got x squared. Let's say I drew a, let's do some right-hand triangles. Okay. Now if I were to change it, and instead of doing x squared, I wanted to integrate 2x squared. Of course, the widths would all stay the same, but the function would get steeper. It would double the size, or the height, of each rectangle. Each rectangle's height would double. Well, if the width stayed the same, but each rectangle's height doubles, what does that do to our area? It doubles it. So if I know the area of x squared from 0 to 3, okay, and it's 9, then the area of 2x squared from 0 to 3 must just be double the old area. It must be 18, and that's this constant multiple. You see that if I have an old function and now I've multiplied it, in my case, by 2, I can just kind of leave the 2 out front and find the area and then double it afterwards. All right? Next, let me grab this one. Sum and difference. I'm mainly going to focus on the difference right now, and we're just going to think about our kind of additive properties later. Let's say I want to find the area inside that little football type shape, bounded by the 2. Hopefully you see that if you found the area under the big part, and then you found the area under the other part, and subtracted it, you would get the area between them. And basically, the sum and difference says if I'm adding two functions together, I can just find the area of the first, the area in the second, and add their areas together. And how we are going to use this one more often is the difference. If I'm finding the difference between two functions, I can find the area under the first function and subtract the area under the second function. All right? Let me do another one, additivity. Let's say I do the integral from -2 to 0 of x squared dx. So I've just found that area right there. And then let's say I find the area from 0 to 1 of x squared dx. So now I've found this area. If I add these two things together, what I've really just found is the integral from -2 to 1 of x squared dx. Because if you take the area from -2 to 0, you take the area from 1 to 2, and you add them together, then what you've just gotten is the total area from -2 to 1. And that's what additivity says. If I have the area from A to B and the area from B to C, then I can get the total area from A to C. Alright? This time I want to draw my own function. So let me kind of just draw a random f of x. Okay, here's f of x. And let's say I want to evaluate the area from 0 to a of f of x dx. If I pick the minimum value, which is right here, the minimum value of the function on the interval, and I make a rectangle. Notice that the rectangle has a much smaller area than the entire function. If I pick the maximum area, or the maximum height of the function, and draw a rectangle, notice that that rectangle, this new black rectangle, has an area much bigger than the area under the function. The max-min property simply says that the true area under the function will be greater than that minimum rectangle, the minimum multiplied by the base, and less than that maximum rectangle. So pretty obvious, I think, that will be true. And finally, the law of domination. Let me again draw myself my own new graph. I'm going to draw a function f of x. Let's just do this. There's f of x. Drop it down, area from 0 to a. Okay. And let me draw another function g of x. Okay. There's g of x from 0 to a, and just like that. The law of domination says that if one function is always bigger than another function, and in this case g is always bigger than f, then the area under g must be less, or must be more than the area under f. And certainly that's true. If you have one function that's always bigger than the other function, then its area will always be greater than the other function's area. That's the law of domination. So pretty easy, and again, these are in the book, but they're pretty easily seen by graph and just focusing on the fact that integrals represent area.